Magnetization. Chapter number 7. Magnetization. In this chapter, the main concern is on the magnetization of the material, the effect of magnetization on the material, the resultant concept of bound currents, and its physical interpretation. We will derive the Amperes Law in magnetized material and introduce the concept of magnetic susceptibility permeability. The chapter also includes the derivation of energy in magnetic field. First topic, magnetization. Consider a piece of magnetic material on atomic scale. Electron orbiting around the nucleus and electron spinning around their axis. These result into the tiny current loops. Each atomic current is a tiny closed circuit of atomic dimension. So it seems reasonable that the distance magnetic field of an atom is appropriately represented by magnetic dipole field. Ordinarily, they cancel each other out because of the random rotation of the atoms. But when the magnetic field is applied to the net alignment of these magnetic dipole occurs, the material becomes magnetically magnetized. And the magnitude of magnetic dipole moment m due to the current loop is given by m is equal to I times of area A, where I is the current of the loop and the A is area of the loop. The direction of magnetic dipole moment is perpendicular to the plane of the current loop. Now, unit of magnetic dipole moment are amperes meter square. These magnetic dipoles, these dipole moments give rise to the property of the magnetic material, and that is known as magnetization. Magnetization, therefore, is defined as magnetic dipole moment per unit volume. That is, capital M magnetization is equal to dm divided by d bound current. Consider a single closed current loop in a material. Magnetic potential equation for these current loop will be A, which we have defined in a before lecture. A is equal to mu naught divided by 4 pi integration current density J divided by R d tau in a prime. The formula for current density J is given by I divided by A, where I is the current and capital A is the cross-sectional area. Infinitesimally small area element d tau prime is area times dl. If we substitute the value of J and the value of volume element d tau prime in above the equation of the potential, we will get potential A is equal to mu naught divided by 4 pi integration I times I divided by A R times A dl. A get cancelled and the equation becomes mu naught divided by 4 pi integration over closed path I divided by R dl prime. To write the potential in the form of power series of 1 upon R, where R is the distance of a point under the consideration, if R is sufficiently large, the series will dominate by the lowest non-vanishing contribution and the higher term will be ignored. Therefore, 1 upon R is actually 1 upon R under root of R square plus R prime square minus 2R R prime cos of theta prime, which nearly equal to 1 upon R. Summation goes from 0 to infinity R prime divided by R raised to n Pn cos of theta prime. If we substitute these value in the potential equation, we will get mu naught I divided by 4 pi summation n goes from 0 to infinity 1 upon n r raised to n plus 1. How it come n plus 1? This 1 upon r outside will come inside, and here we have r raised to n. So r raised to n plus r, that is r raised to n plus 1. Summation over closed path r prime and pn cos of theta prime dl prime. First term of this series, which is 1 upon r, because n equal to 0, that is 1 upon r only, is monopole. But in magnetostatic, there is no possibility of monopole. Therefore, it will vanish. The second term of the series, which is 1 upon n equal to 1, that is 1 plus 1, 2, 1 upon r square. And this is for the dipole. Similarity, the third term for quadrupole, and so on. Therefore, we will concentrate on the dipole. And for the dipole, we have magnetic potential as A equal to mu naught I divided by 4 pi r square integration over closed loop r prime, since n equal to 1, r prime cos of theta prime dl prime. Now think about this r prime cos of theta prime term, that is the integration term, which is equal to r prime 1 cos of theta prime. 1 cos of theta prime is r cap, that is the position vector of this point with respect to origin O. That is, we will get r prime dot r cap in the equation of the potential. Now, basic formula is integration over closed loop r prime r cap dl is nothing but r cap cross product with integration of area dA. We will substitute in place of the integration term as the integration of area cross product with the r cap. Now this is the total area, that is capital A. Now, if you look closely, you will find that mu naught divided by 4 pi r square, and this I into A term. This is, we have magnetic dipole moment, which we have defined in the start of the lecture. That is M. Cross multiply with the r cap. Now, above equation shows the potential due to the single dipole moment M. But in magnetized material, each volume element delta prime carries a dipole moment M prime. Now, M is magnetization into volume beta dash prime. So, total vector potential A is equal to mu naught divided by 4 pi M, rather than M integration of magnetization vector M r cap r square 1 upon r square over the volume beta prime. Now if you closely look, this r cap divided by r square, this is nothing but the gradient of 1 upon r. If we replace it in the equation, we will get vector potential A is equal to mu naught divided by 4 pi integration magnetization cross product with the gradient of 1 upon r d tau prime. Now, using the integration by part and the product rule, we will have this term into the two parts, that is two terms. 1 upon r del cross magnetization over the volume d tau prime minus del cross magnetization m divided by r d tau prime. Now applying a basic formula that Integration del cross P d tau prime is nothing but minus of integration over a closed path area P cross n cap dA on the second term of the equation. We will get vector A is equal to mu naught divided by 4 pi 1 upon r del cross m d tau prime in minus minus get plus 1 upon r m cross n cap over the area dA closed area dA. Now this formula is derived in below to this PDF. First term of the equation shows the potential is due to the volume bound current, and that is JB, which is equal to del cross M. And the second term of the equation shows the potential is due to the surface bound current, that is KB, which is equal to M cross N cap. Now if we replace these two terms by JB and KB, we will get potential A is equal to mu naught divided by 4 pi integration JB divided by R d tau prime plus integration over closed area KB divided by R A prime. Now physical interpretation of bound charges. Consider a tiny slab of magnetized material of a thickness d. The induced magnetization is due to the sum of the atomic dipole moment m induced due to the each atom of the substance. Now, each dipole moment is due to the closed loop of current in the surrounding of each atom. In case 1. If the magnetization is uniform, the current in the various loops tend to cancel each other, and there is no net effective current interior of the magnetic material. But current at the surface is not cancelled. As you can see, it is not cancelled. And this gives rise to the surface current density Kb. Let A be the area of the current loop, and its dipole moment in terms of the current I is m equal to I times of A. Magnetization due to this dipole moment will be m equal to small m divided by area A into the thickness P. Now, small m therefore is equal to I times A, which is equal to m times ABA. AA get cancelled, and we will result into the equation that I, the current, is equal to magnetization into the thickness T. Surface current density is the current flowing through the surface per unit length. Now, if I divide KB equal to I divide by D of above equation, we will get M. That is, KB is directly equal to M. Now, the direction wise, if we express, the vector KB is equal to vector of M cross product of N cap. Case 2. If the magnetization is not uniform, the internal current no longer cancel each other. There are two figures, and you can see that there is two adjacent chunk of magnetic materials. On the surface of x direction, the current rises due to the variation of magnetization in y direction, and as well as due to the variation of magnetization in z direction. Consider the two chunks of the volume element dx, dy and dz. A net current in x direction is given by I zy which is the variation of magnetization in Z. Therefore, mz y dy minus mz y dz, which is nothing but partial derivative of mz divided by y dy dz. Now, if we divide this dy dz below the I zy, we'll get di zy dy dz is equal to partial derivative of mz divided by dy, which is nothing but jb at yz. The similar way, if we consider the variation along the z direction, that is current yz is equal to minus of, since it's reverse, minus of myz is z minus myz. Total dy, junk volume is dy. Again the same formula will repeat and we will return as jb yz. Therefore, the total current density in x direction is due to addition of jbyz and jbzy. Now we know jbyz is minus of dy by deba my by deba z, and jb zy is deba mz divided by deba y. If we put this value, we will get the current density jb in x direction as deba mz divided by deba y minus deba my divided by deba z. Now this is the actual term of x component of del cross m. Now that result and that shows that jb vector is nothing but del cross m. Now taking the divergence on both the sides, and we know del dot j is equal to 0. Similarly, divergence of a curl is equal to 0. This shows that the divergence of a bound current density is 0. Next topic is Amperes Law in magnetized material. Now, total volume current within the magnetized material is due to the bound current, due to the magnetization, and due to the free current, due to the free flow of the electrons or charges. Therefore, the total volume current density having two terms, Jb plus Jf. Now, Jb is del cross M, whereas Jf we have known, J we have known by the Ampere's law, mu naught J is equal to del cross B. If we substitute the value of J and Jb in above equation, we will get 1 upon mu naught del cross B is equal to del cross M Jf. And if we move this del cross M terms from right to left, we will get 1 upon mu naught del cross B minus of del cross M equal to J. If we take del cross common term outside, the del cross, we will get B by mu naught minus M equal to J. Now let this term to be known as H. That result, del cross H is equal to J. And this is the Ampere's law in magnetic material under the differential form, where H is known as auxiliary field. Now, taking the surface integration on both the sides and by applying the Stokes theorem on the left side, we will get del cross H is equal to integration over a closed path H dot dl, and integration of Jf df is equal to free current IF. We will substitute the values in above equation. We will get integration over closed path H dot dl equal to IF. This is the Amperes Law in a magnetic material under the integral form. The unit of auxiliary field H is given as amperes turn per meter. Now, magnetic susceptibility and permeability. For most of the substance, magnetization is directly proportional to the auxiliary field. And when the field is sufficiently small, and hence for the linear isotropic homogeneous material, magnetization is directly proportional to the auxiliary field H. And this proportionality sign is replaced by proportionality constant Im, where Im is known as magnetic susceptibility and it is dimensionless constant. We know that H is B by mu naught minus M. Now, if we replace this M by Imh, then we will get B by mu naught minus Imh is equal to H. That result, B by mu naught is equal to Im plus H. Now, if we take H as a common factor out, then we bracket make Im plus 1. Now, this Im plus 1, let it to be known as the relative permeability of the medium. And it is also a dimensionless constant. Therefore, we will have mu naught mu r, and that mu naught mu r, let it be mu, which is the magnetic permeability of the linear material. And it has the same unit as a mu naught, that is Newton per meter square. Sorry, Newtons per ampere square. We know that bound current density Jb is equal to del cross M. And what we have defined M is a chi H. Therefore, del cross Jb is equal to del cross chi H. If we take cross product of 1 by 1, that means del Im del cross H minus H gradient of Im. Now, Im is a constant quantity, therefore it will result into 0. But del cross H is not a constant quantity. It has a value of Jf. That means Jb, bound current density, is directly proportional to Jf, and that proportionality sign is replaced by a constant Im. This shows that the volume current density of a bound current is directly proportional to the volume current density of a free current in a linear medium. Energy of magnetic material. Now, inductance is the tendency of electrical conductor to oppose the change in electric current flowing through it. The flow of electric current creates the magnetic field around the conductor, and the field strength depends upon the magnitude of the current and the flow any change in the current. The changing current induces a voltage in the conductor, and this induced voltage is in the direction which tend to oppose the current, and it is called as a back EMF. Let L, the inductance, is that it is a ratio of between the induced voltage and rate of change of current. That is, E is equal to minus L di by dt. The current flow through the inductor L produces the back EMF. Work done on a unit charge against the back EMF in one trip of the circuit is minus of E. The negative sign indicates that the work done is done against the EMF, not by the EMF. The amount of total charge per unit time passing down by the wire I. So the total work done per unit time is dW divided by dt is equal to minus of EI. Now where we have a E equation is a minus of LdI by dt. If we substitute that, minus minus get cancelled, LI by dt. Integrating over the time on the both side, we will get W equal to 1 by 2 Li square. The magnetic flux is given by phi equal to integration over a surface B dot dA. B is what we known as a del cross the potential, magnetic potential A. If we substitute that value in B, we will have a flux is equal to integration del cross A is equal to del cross A dot the area dA. Now, when we apply the Stokes theorem, we will have a flux phi is equal to integration over a closed path A dot dl. If the current through the closed loop is I, and the phi will be L times of I, and we will substitute this value L times of I in above equation. L times of I is equal to integration over closed path A dot dl. Now what we have find the work done? Work done is equal to 1 by 2 Li square. Let it be 1 by 2 Li I. Now Li we can replace by above equation, which is nothing but integration over closed path A dot dl into I. Now as you can see from the figure, I dl is nothing but J times of d tau. Now J we know as by the Amperes law, it is 1 upon mu naught del cross B. Then we substitute in the value, we will have work done W is equal to half integration magnetic potential A 1 upon mu naught del cross B d tau. Now, if you see the integration term and if you make arrangement of del A dot del cross B as a del dot A cross B, which is equal to B dot del cross A minus A dot del cross B, and this A dot del cross B is same as our integration term. Therefore, A dot del cross B, if we take it toward the left hand side, and whatever we have a left hand side as is del dot A cross B to the right hand side, and then substituting this equation in above, we have two terms. Now, if you see closely this term del cross A, this is nothing but B. We know by the definition of vector potential in magnetization, del cross is equal to B. Del cross A is equal to B. That means A dot del cross B is equal to B dot B. That is B square minus del dot A cross B. Now substituting this equation B square minus del dot A cross B in work done equation, we will have work done equal to 1 upon 2 mu naught integration B square minus del dot A cross B d tau. Now, if we take divergence theorem over here, so we will have integration over closed area A cross B over the area dA. As you move away from the current flow, this A and B both terms decreases such that the surface integral over all space becomes 0. Second terms get vanish, only first terms remain. That means W is equal to 1 upon 2 mu naught integration B square over the volume d tau. Now, current density of the magnetic field is given by dW divided by d tau is equal to B square divided by 2 mu naught. A useful formula which has been used above but not proved before, we have included over there here. A useful formula del cross P theta is equal to minus of integration over a closed area P cross n cap. Now some of you says that we might have applied the Stokes theorem. No, we have not applied the Stokes theorem. It is something different. Now consider the product, a vector product P cross C. C is a constant quantity. Therefore, del dot P cross C is equal to C dot del cross P minus P dot del cross C. Now, since C is a constant quantity, the cross product of with del is equal to 0. What we remain, del dot P cross C is equal to C dot P del cross P. Now, taking the integration on both the sides with respect to volume, we will have integration del dot P cross C is equal to P cross C over the volume d is equal to integration C dot del cross P over the volume d. By applying the Gauss theorem over here on the left hand side, we will have integration del dot P cross C beta is equal to integration over closed area P cross C n cap dA. Now, if you look this term very closely, this is what from we got left hand side replacement. Okay, but P cross C n cap is nothing but n cross P C. We have make it circle. That is n cap cross product P dot C. अगर C को यहाँ लाना है तो we have to put minus sign. C dot n cap cross P. Therefore, we substitute this value in above equation. So we will get integration C dot del cross P over the volume beta is equal to minus of integration over closed area C dot n cap P cross product with the P. Now, C is an arbitrary constant. We can cut it out from both the side and we will have final equation as a minus closed area integration n cap cross P is equal to integration del cross P d tau. And these are our bibliography used for above